everyone, quite the crowd here. As Kostas mentioned, my name is Amey. I work on the marketplace data intelligence team at Uber. Our team builds some of the critical geospatial data systems upon which some of our crucial real-time algorithmic decision engines are built upon. These are the engines that drive our ride-sharing marketplace. And today I'm going to talk about how do we sessionize Uber trips in real time. So agenda for the talk, brief introduction to the marketplace organization at Uber, some of the sessionization use cases, what are the unique challenges we face before delving into the anatomy of what constitutes an Uber session, which is the state machine, the Scala DSL we wrote for describing the state machine, and finally, going to discuss the painful lessons we learned running sessionization pipelines in production. So on Marketplace, we're a bunch of engineers, data scientists, and economists working on some of the hardest quantitative problems involved in optimizing a ride-sharing marketplace in real time. To that end, we have well over a dozen teams, but some of the more prominent ones are in this slide. For instance, in dynamic pricing, these guys control the pricing levers in order to optimize the supply and demand in real time. We have the intelligent dispatch. These guys, match riders and drivers optimally to ensure lower wait times and, deliver the perfect Uber experience. We have Marketplace Health. It's a team that monitors marketplace health as it regards to business metrics over time. We have a forecasting team whose job is to forecast different marketplace dynamics over both short and long-term horizons. And finally, we have the marketplace platform that sort of orchestrates the core trip flow. A lot of these teams, say for the platform guys, rely on systems built by my team. So what's a marketplace? In a context of a city, you can think of it as a microcosm of an economy, in a sense that you have thousands of riders and driver partners interacting with each other. They're essentially bidding on price of a ride, and they're giving rise to a marketplace. To that end, for a lot of what we do, we end up having to describe models for the real world and decision engines that act upon these models. What do I mean by that, right? So in our use case, we end up having, real-time events that are occurring in the physical world. These events drive marketplace dynamics. Marketplace dynamics are things like supply, things like forecasts, things like trips. These things affect the algorithmic engines. That's, like the dynamic pricing algorithm, it's the dispatch algorithm, and these algorithms in turn influence real events in the physical world. It's a continuous feedback loop. The real events here mean like, traffic patterns. These things could be demand patterns. There's a sporting event, and suddenly at 6 o'clock in San Francisco outside Giant Stadium, there is a massive spike in demand. So these are sort of the problems that we're trying to optimize, essentially to be able to deliver you an Uber ride in a timely fashion and, more importantly, an affordable fashion. So where does sessions fit into this, right? We are a company famously built atop an architecture of a few thousand microservices. What ends up happening, in practice is that a singular trip request will span multiple, in some cases like 30, 40 service boundaries. So what ends up happening is we end up distributing the context around a singular trip across many, many different event streams. So it's the job of the sessionization pipeline to contextualize these event streams and make them available to any downstream system in real time, in near real time. So we need to really not only keep track of rider state, we also need to be able to deliver this to downstream algorithms in sometimes second-level latency. Apologies, the slide is intentionally vague, but yes, we have algorithms that need to adjust to spikes in demand and balance the supply of drivers in a marketplace in near real time. We also have like some machine learning models that need information about pre-request activities in real time. To give you a data point, every time you open an Uber app and you enter a destination and you have a request, this probably takes a few seconds, if anything at all. And we need to have, like live sessions data for this use case. It's not just for live use cases. Sessions also powers a lot of business intelligence and operational analytics at Uber. This is what our operations team calls a rider experience funnel. The green boxes are the happy path. The rider opens the app, they get to the request screen, they have a request, we dispatch a car, and they complete a trip. That makes Uber very happy. However, we also have the drop-offs from this funnel. A rider could exit the app pre-request. They could cancel pre or post-dispatch. It could be unfulfilled. The product type you're requesting, we just don't have a driver partner with that product driving in your area at that given time. Also, a driver could cancel. So this is our view of the rider experience with the Uber app. And this sort of nicely dovetails with our definition of a session on the marketplace. Yeah, so sessionization has been around ever since, Yahoo days, right? So what's so unique about sessions at Uber? We're famously a two-sided marketplace. Our session state machine needs to model interactions between riders, our driver partners, and our backend systems. And at least two of the participants in this transaction are sentient beings, and they're moving in space and time. And this especially causes problems with assumptions you might be making. So what is a Uber session? So when you open the app, you're presented with a destination selection screen. This is a choose destination state, as we call it internally. Here, nothing interesting is going on here. You just select the destination you want to go to. And once you have selected the destination you want to go to, you enter the shopping state. This is the product selection screen. It looks fairly benign, but there are a lot of things going on here. So let me unpack that for you. For instance, yes, so you were displayed 3 products for your given geography, so interacted with our product service. So here you're looking at products in San Francisco, UberX, Uberpool, and ExpressPool. You were shown 3 prices here, so you interacted with dynamic pricing system and you interacted with the upfront pricing system. So you could see 3 prices here. You're shown like 3 ETDs, which are called estimated time to destinations. So you interacted with the ETD service. There is 1 ETA being shown on the map here, and that's the ETA for the pickup for the UberX in this particular situation. And by the way, this is just like one snapshot of what's going on in a shopping state. As you're on the screen, events are changing dynamically. And our sessions state machine needs to record all these different discrete bits of information correctly and hopefully in order. But obviously, with streaming systems, there's only so much order you can guarantee. So you select a product, you make a request. At this point, you're interacting with payment service because we want to make sure you're good to pay for the ride. And the dispatch service, the dispatch service will try to match you with a driver partner close by. You could, as a rider, after a successful dispatch, you could still decide, hey, you don't want to take this ride, and you could cancel, sowing discord and unhappiness in our marketplace, but still okay. We charge you $5 sometimes if that annoys us. However, or you could wait for your driver partner to show up, and once there is a successful pickup here, in the real world, our session state machine needs to transition onto the on-trip state. This is the happy path here, and an on-trip state invariably leads to a session ended on a completed drop-off. So from beginning to end, our session starts with the time you open the app to the trip complete, or with 30 minutes of inactivity. So essentially, this is like a dynamic gap, a session window with a dynamic gap. So how does our implementation look like? So after quite a bit of fiddling, we settled on this very simplistic simplistic concepts of a condition, a transition, and a state. This is our internal state, not the Flink state. A condition maps a incoming event to a Boolean. A transition is made up of conditions that trigger it, and a method that computes the next state, given current state and the incoming event. We have an example of what sort of transitions you can describe. This is the request ride transition. It has to be a request type event, and rider has to be looking for a ride. That's what the condition is saying. And it's pointing to another method that computes the next state. This is our notion of a state. It has quite a bit of metadata, but it also has a list of transitions. These transitions are evaluated in order. So each incoming event is run through these transitions, and the first event to validate a condition for their transition is that transition is the one we trigger. So yeah, this is the example of how, say, a request write state would be put together with this DSL. Essentially, we have a list of transitions. A request writes major transition is to transition to on trip. You could transition back to shopping because these are transitions for request expirations. So yeah, our original pipeline was written in Spark streaming. And at Uber, we have been moving our streaming use cases to Flink over last year. It was relatively easy for us to move to Flink. In Spark world, we used to manage our session windows ourselves. In Flink world, you have nice abstractions like event time session windows with dynamic gap. We needed to write our own evictor, but that's because we do a crazy secondary sort. And we could just move our Spark state function as is. It was just a copy paste job there, and we were good to go. So this is the most interesting part of the talk. It's actually fairly trivial to write sessionizing pipelines or session windows here. However, no one really talks about the things you're likely to encounter, when running these things in production. So I'll run through some of the painful lessons we learned running this stuff. All right, well, the major lesson was time is relative and clocks are hard. What do I mean by this? Well, our state machine models interactions between riders, drivers, and internal backend systems. Each of them have their own notion of time. And time is very messy in the real world. I've seen phones that are back from the future. I've seen phones that think the time is 1970. And there is no good way to trust any client-side timestamp. So to get around this, we had a very simplistic fix. We just decided to use Kafka timestamp, the timestamp when an event is pushed to our Kafka cluster, as our event timestamp. However, this presented us with another problem. Our client-side logging is buffered, and essentially what happens is we see a torrent of or a batch of events that share the same Kafka timestamp, but they have increasing client timestamp. So we need to essentially keep track of per key watermarks. Here we're essentially sorting events for a particular key by their own client timestamps. So even if they think it's 1970, we hope that those events are coming in in correct relative order. Moving on to checkpointing. Yes, so checkpointing, we have always found this you cannot always rely on this, right? Like your HDFS might freeze sometime. And also it really depends on what level of back pressure your downstream applications can tolerate. In our case, it's always rush hour somewhere. And if your back pressure the pipeline takes like 30 minutes to catch up, it's probably good for most sessions use cases, but not so for us. So sometimes it's just easy for us to store per key state to Kafka, and then restart a new pipeline and store from this partial state instead of relying on checkpoints or anything else. Yes, we are reading the latest events from a partial state, but it's still better to give partially incorrect answers to downstream systems sometimes than no answers at all. Of like, hey, how many people are looking to get an Uber ride in the world right now? So we just let Backfill take care of any gaps. That brings us to the next pain point, which is Backfields. Backfields can actually introduce subtle bugs because they are counterintuitively more correct. What I mean by this, like Backfields allow you to reorder events over larger time windows. This essentially causes problems for us because our downstream index is Elasticsearch, and we index documents by a session UID, which is composed of an anonymized writer UID and a session start time. So if your backfill reorder events even slightly, your session now might have a different start time, and you might have two nearly identical sessions, which have slightly different start times, which really is of no use to anyone, and you end up corrupting your index. This is like a personal pet peeve of mine. I think no framework has ever handled this correctly. Our products are constantly evolving, and our state machine needs to change along with it. However, you just can't like run a new pipeline without the state having warmed up. And in our case, we need to run it for a few hours before we can reliably trust it to run. Or trust it to write to our production indices. Yeah, it would be nice if you could just run a pipeline with a ad hoc state. But yes, so what happens in practice is we have a carefully choreographed handoff where a old pipeline needs to be drained, meaning all the sessions it has in memory, they need to be written out. Because yeah, remember, you could have a session that started right now that the old pipeline's keeping track of, but it could end a few hours later, because again, this is a dynamic gap, and however, your new pipeline warmed up in 2 hours, so it's writing sessions that started at that 2-hour mark. So these two pipelines need to run in sync for a while before you can reliably switch the old one off. So that's been a constant pain. This point is very obvious, but bears repeating. Your world will change from underneath you. There's always going to be some team that's going to change that's going to destroy your definition of session by pushing some change. So keep track of every metric you can possibly think of. The data metrics, the data quality metrics rather, the business metrics, and your app internal metrics. We use M3, which is our open source metrics platform for Prometheus. Lastly, imputing state. So if anything I want you to take away from this talk is that when you're trying to enforce a state machine to real-world events, you can never anticipate all the edge cases that will happen. The long tail of unexpected events is really really long. Best advice I can give you here is make sure your state machine is flexible enough to incorporate these. Like the state machine design should be iterative. So keep track of states that have a lot of no-ops that usually is a sign that maybe you should break that state into 2 states to model, events correctly. And lastly, our mobile logging is buffered, and in geographies with low network bandwidth and low tech phones, events will be dropped. What do you do? What do you do with dropped events, right? However, your state says, hey, the rider is shopping for a product, but your dispatch system says, hey, someone already picked up this rider. All you can do is you can impute that, yes, they probably requested and we dropped the request. So you need to, have notion of super events. Ideally, all events are equal, but some events are more equal than others. So do identify these super events and use them to force transitions in your state machine. You can later on impute those transitions, and not all transitions have the same quality of information. So sessions in numbers. So yeah, we ingest tens of billions of events daily. We generate tens of millions of sessions. We are finishing our move to Flink. Unfortunately, I wanted to have some numbers to compare, but we haven't officially productionized our Flink pipeline yet. It's running in shadow mode. So yeah, that was all I had. Yep.
Thanks, Amey, for the talk. Do we have a time for a couple of questions?
You mentioned the checkpoint to HDFS is unreliable. Can you elaborate a little bit?
Oh, well, it's probably more to do with Uber's. Well, we have our own infrastructure, and we have a shared HDFS. It doesn't have 4.9's level of guarantee. And this is probably an unfair knock on Flink, but this is more to do with our experience with Spark streaming. Checkpoints could get corrupted, or recovering from checkpoint, or reading just like a terabyte of state from a checkpoint would take lots of time. And as I mentioned, some of our use cases have second level requirements. These are not like enforced SLAs because even though teams would like that, we were like, you literally cannot expect this SLA because this is how the world of streaming works. But we try to bring our job back up as soon as possible. So yeah.
You said that you keep watermark per key.
Correct.
As far as I know, Flink cannot do that. Can you elaborate on that?
Flink can do that, or Flink cannot do that? Oh no, we do that on our own. So we're keeping track. So as I mentioned, the problem is every client has its own clock, and that clock cannot be relied on. So we need to keep track of watermark so Flink's watermark is a global watermark, right? So you need to have all events sharing the same clock. So that is our Kafka timestamp. But once you have that, you still have events that, because our client logs are buffered, So those Kafka timestamp, the increasing Kafka timestamp does not guarantee an increasing client timestamp. They could be in the reverse order. So you need to, again, go ahead and then sort them on those client timestamps. So that's literally just keeping track of the client watermarks. So.
Hi.
Hey.
Thanks for the talk. Even though it can be quite obvious, can you elaborate on the reasons you switched from Spark to Flink?
Right. So, well, Spark streaming is not supported at Uber. We were running the pipeline secretly, so that was the most obvious reason to move to Flink, because that is the blessed system. And the other thing was, operationally, we didn't, like, there were only 1 or 2 people at the company who would know, who know about how to work with Spark streaming. So it just made sense to move to the platform that's actually supported. And having said that, there were other reasons too, right? Like, because in Spark world, you're just dealing with batches. You don't really have notion of session window. So we were doing that calculation on our own. So we could be wrong, which would mean I wrote bad code. But now if our session windows are wrong, I could blame Flink. So that's also very good.
I think we're short on time. Are there any more questions? Super. Nice. So thanks, Amey. And we can take a short break and see you next.